I work in the JDK core libraries team at Oracle, and one of the things I work on is the collections framework, and so that's what I'm going to be talking about today. I wanted to mention a couple things. If you want to get in touch with me, you can see on the slide my Twitter handle, @Stuart Marks, and I've also created a hashtag for the subject matter, and so if you tweet with the hashtag collectionsrefueled, then I will monitor that and look for questions, and if I get a chance, I will answer questions on Twitter. All right, let's start off with a brief history of the collections framework in Java. So when Java was introduced in JDK 1.0 in 1996, it didn't really have what was called the collections framework. It did have what we now call the legacy collections, which are vector and hash table, or since the capitalization was off, people call this hashtable. But you can really see if you look at these, you can see that they're legacy, because hash table is a class. It's not an interface. And so what happens was that programs that use those use concrete implementations. And so in JDK 1.2, introduced what we now call the collections framework as a family of interfaces, and that really changed the way you programmed using collections. Much for the better, I think, because instead of passing around, if you wanted to use something other than a hash table, you had to change which implementation class you used, and you also had to change all of the APIs that used it. And so in 1.2, a family of interfaces was introduced, the ones that are still used very heavily today: collection, list, set, and map. And so I think that framework of interfaces continues to serve us well today, even nearly 20 years later. Also introduced were new families of collection implementations. And the most popular and heavily used collection implementations that were introduced all the way back then are ArrayList and HashMap, and those are still the most frequently used collections today. Okay, moving forward in Java SE 5, a bunch of new changes were made to the platform. The ones that impacted the collections the most were the introduction of generics. And so generics were retrofitted to all of the collections interfaces and implementations. And then also a new package came in, Java Util Concurrent, which added, among other things, a set of collection implementations that were thread safe or that were concurrent, that in fact allowed multiple threads to interact over the data structure at the same time. And so concurrent hash map is quite frequently used data structure that was introduced back in Java 5. I won't really be covering the concurrent collections in this talk, but to just to let you know that they're there. And then in Java 8, of course, many people are familiar with streams and lambdas, but another language feature was introduced in Java 8, which was default methods. And so what that allowed us to do was to enhance existing interfaces in a compatible way. And so we added a bunch of default methods to those now almost 20-year-old collections interfaces. And what that did was, since we added new methods to those old interfaces, every existing collection instantly got new functionality. So if you have a collection, no matter when it was written and compiled, you can call the stream method on it, and you can get a stream out of it now. So that's very powerful. So that wasn't really an enhancement to the collections framework itself, but it was an enhancement that allowed the collections to participate fully in the new Java 8 streams world. All right. So here it is, almost 20 years later after the collections framework was introduced, and I think it's still going strong. It's still heavily used today, used daily in programming, and still useful and I think well designed. And the design has served the test of time. And what's interesting about this is that we are still evolving the collection framework. In fact, I see changes being proposed on the OpenJDK mailing list about how to continue optimizing even old classes like ArrayList and HashMap. And in fact, HashMap has probably been rewritten twice since it was introduced back in 1.2, and it's gotten faster and more powerful each time. And so we are still continuing to evolve and optimize the implementations. All right, so what the bulk of this talk today is about is Java 9. So we've added some enhancements to Java 9, including some new collections APIs and implementations. And so the official name is the collections convenience factory methods. And so basically it's about factory methods that allow you to create new collection instances conveniently. The main goals of this effort were to provide a convenient and concise way of creating collections, but they are also space efficient, and I think they are also unmodifiable. And that's a theme that we are continuing to pursue with future versions of Java. The theme of moving away from mutability and towards unmodifiability and immutability. I think that's better for concurrent programming, and it's better for functional programming. So we're introducing stronger support for unmodifiable collections, and I think those will be more frequently used in the future than they have been in the past. All right, so quick rundown of what the feature is. So this is an API that exists only at the library level. There, basically, new static methods were added to the list, set, and map interfaces. That's another new language feature introduced in Java 8, which is the ability of interfaces to have static methods. So we're taking advantage of that by adding static methods to list, set, and map. We did not change the programming language to allow for collection literals. There are several other programming languages that have a dedicated syntax to creating instances collections, and we have considered doing that in the past in Java, but we decided against it. And mostly it was pragmatic. I think ultimately the language probably would be better off if we had the time to do a good job with adding collection literals to the language. But in fact, doing that is very expensive because designing a language change is much more difficult and requires a lot more thought and careful review in order to retrofit language syntax into existing programs. But also, what it does is it does something very interesting, which is it creates a tight coupling between the programming language and the collections framework that we have. And so if you look at what Java has today, the collections framework that was introduced in 1.2, it rather stands at arm's length from the programming language. There's not a tight binding between the programming language and the collections that exist in java.util. And if we added collections literals, then we would be making a very tight binding between them. And so that would mean that whenever you wrote a collection literal in your program, you would be talking about specific collections implementations in java.util, and we were very, very uncomfortable doing that. Now, we could have done more work and added another layer of indirection and have like a factory for collections literals that indirected through something and delegated it to some collections implementation, so that in the future we could use collection literals to create instances of other collections, or you wanted to add a third-party library that would use the nice hypothetical collection literal syntax to create instances of its own collections. Well, that would add even more complexity and add more time to the delivery of this feature. So ultimately, it was felt that that was just too much work for actually too little gain. And so what we did in Java 9 was, OK, just add some library APIs. It's pretty easy to do. We know how to add static methods to interfaces. Let's do it. And so that's what we did. All right, so what static methods are these? So basically, it's a large family of methods called of that take 0, 1, 2, up to 10, or many, or var args elements. So there's list.of with no arguments creates an empty list. List.of with 1 argument, 2 arguments, and then up to 10 arguments, and then a var args overload. And then similar with set.of with 0 through 10 and var args. And map.of. Now map is a bit different. I'm going to discuss this at length, but the difference between map and things like list and set is that map has keys and values that are of different types. So you can't retrofit the obvious var args onto the end like you can with list and set. And so what we did was we said map.of with fixed numbers of pairs of keys and values, up to 10 pairs of keys and values. But then for var args, if you want to create a map instance with an arbitrary number of key-value pairs, we do provide a varargs method to do that, but it has to be different because keys and values have different types. So what we did is we added a different method called map.ofEntries that takes a varargs parameter of map.entry references. And then just to make that a little easier, we have a convenience method map.entry, lowercase map.entry, which creates an instance of uppercase map.entry. Sorry, that's hard to read, but when you program it in code, I'll show some examples later on. It actually makes a lot of sense. All right, so I mentioned that we have fixed arg overloads for up to 10 elements or key value pairs. And so this is what the API looks like. And you can see this is a snapshot of the Java doc. And it's like, wow, you look at this, and it's like, oh, this is really terrible. And it's pretty amazing what kind of reception this gets from the general public. Because when this API was posted, the discussion broke out on Reddit. And somebody said, is this a joke? So it's like, OK, yeah, so this is the kind of technical review we get for APIs like this. OK, so the reason that there are so many fixed arg overloads is that when you call a varargs method in Java, there's no built-in facility for stepping through a variable number of arguments. All the compiler does is say, OK, you took a certain number, you provided this. The syntax allows for a variable number of arguments, and the compiler just says, OK, I'm going to take those arguments and gather them up into an array, and then pass the array. And so when you receive varargs, you get an array of the number of args. And that's nice because you can look at the length and so forth. But that unavoidably does two things. One is it allocates memory. And the second thing is that I forgot the second thing, what I was going to say. Anyway, but it adds overhead. Oh, that's right. It adds copying overhead, right? So first the arguments get copied into the array, and then when the collection is created, the elements have to be copied out of the array. So the fact is, it adds memory allocation and copying overhead. And so you might think, won't this get compiled away by the JIT? Well, probably. If you call these methods inside a tight loop, the JIT will compile it, inline everything, and possibly even avoid allocating the memory. But actually, the main use case for these is initialization. And initialization happens only once. So the fact is that initialization code, especially static initializers, often run in interpretive mode. And so the interpreter does exactly what you tell. Oh, you want to allocate an array. OK, I'm going to fill it in here, and there's your array, and then I'm going to fill them back out. And that's very slow. So we felt that adding a bunch of fixed arg overloads would just put the arguments directly on the stack and then dispatch to the method that knew exactly how many arguments were there. And that avoided the array allocation and copying overhead. So that's the reason for this. So it looks bad in the documentation. It really does add a bunch of clutter, but it shows the complexity of having all of these simply does not show up in your code. You just don't see it. What happens is you call one of these methods, and the compiler will select the right method, and your code is very clean. So what it shows is that we're willing to put in a certain amount of messiness in the APIs in order to enhance performance and in order to make your code look better. All right, so let me show you some examples of how this works here. So the use case here is let's talk about creating an unmodifiable list with a few elements. So in Java 8, you might do that by, well, I'll read this from the inside out. You can say arrays.asList, and that gathers up a certain number of arguments, and then wrap it inside of a collections.unmodifiable list. OK, and then assign that to something. Now in Java 9, it becomes much simpler. You just say list.of a, b, c. So that's pretty nice. All right, a set is pretty similar. The problem is there's no varargs way of creating a set like there is with arrays.asList. So you use arrays.asList and then copy it into a set and then wrap that set with an unmodifiable set wrapper and then assign that to the variable. But in Java 9, you can simply say set.of a, b, c. So that's pretty nice. All right, so with map, now here it gets a little more difficult. And people have come up with all kinds of contortions to get around this. So, but probably the most straightforward way to do this in Java 8 is to create an empty hash map and then call put repeatedly, either on multiple lines or maybe within a loop or something, and then wrap that with an unmodifiable map wrapper. And so that's kind of a mouthful. To put 3 entries, you have to use 5 lines of code, and it's a little bit clunky. And so people have pressed hard on this and come up with some really bad ways of trying to reduce this, such as the dreaded double brace initialization technique. And so if you haven't heard of it, forget that I ever mentioned it. If you have heard of it, don't use it. And this technique has been around and has been debunked for years. And so I'm serious. Don't use it. But the fact is, it keeps coming back. Like on dzone just a few weeks ago, somebody posted another article. It's like, oh, hey, there's this great double brace initialization thing. Here's how it works. It's like, no, please don't do that. And fortunately, in Java 9, there's no need for it at all. Because you can simply say map.of A1, B2, C3. So you can see the alternation between the types here. Strings, or the keys are strings, and the values are integers. And so they alternate. And so you can have up to 10 key value pairs passed to map.of. All right, what happens if you want to have more than 10 key value pairs in a map that you're initializing? So here what we have to do is wrap up each key value pair in an intermediate data structure, which is a map.entry. And then we just call the entry method to create one of those from 2 items. If you're familiar with this already, you might have done something like new abstract map.simple immutable pair, or simple immutable entry, which is quite a mouthful. And so this effectively does the same thing, but it's much easier to type and much less cluttered. Anyway, so what you can do here is you can have an arbitrary number of map entries, and you just introduce them with the entry method that takes a key and a value. So here I have, I don't know exactly how many there are, but I think there are more than 10. In this example, it reads pretty well. There is a bit of clutter with the extra method calls, but you can easily tell, oh, OK, I know exactly what the keys and values are here, because this is a mapping from some character token to some, presumably some enum value that you might write into a parser or something like that. And so anyway, so this is a var args method, so it does bear some additional overhead of both packing the key and the value into the map.entry structure and then putting those into an array, which must then be unpacked into the map. So yes, so that's unavoidable. I think this is the best we could do given the constraints. But it does have the advantage of being fairly easy to read, and it is type safe. And so if you mistype something and mix up the keys and the values, you'll get a compile time error. And we like it in Java when errors like that occur at compile time, so you don't have to you don't have to suffer debugging of code later on or figuring out why your test failed. All right, so that's the basic introduction to it. The APIs themselves are pretty simple, but what's going on underneath is a lot of stuff. And so there are 6 characteristics of the new collections implementations that I want to cover. And so here they all are, and I'm just going to step through them in the subsequent portion of this talk. All right, so first is that the instances of collections returned from these APIs are all unmodifiable. So that means, so in Java parlance, if you have an unmodifiable collection, what that means, all the collections interfaces still have the mutator methods on them. So you can say, list.add or list.remove or something like that. And so if you have an unmodifiable collection, then attempting to add, set, or remove elements from such a collection will result in an unsupported operation exception. So there are a variety of reasons why this is, which is a little bit beyond the scope of this talk. But we do not have separate interfaces for what are, in essence, read-only collections. That's something that people have asked for over the years, and I think it deserves a better answer than I can give kind of on the fly on stage. But I think I need to write an article about that. But it's sort of obvious gee, let's add a read-only collection interface. But when you try to do so, it actually will drag you off into the weeds. So it seems like it's one of those things that's pretty obvious to add, but it is in fact not. So there are no read-only collections interfaces in the JDK. What we have instead is we repurpose the same collections interfaces, list, set, and map, for modifiable and unmodifiable collections. And in practice, I think that's OK, because usually, depending on the context of the program, if you get a collection from somewhere else, implicitly, that's read-only. Somebody hands you a collection, you're not going to modify their collection. You're going to read the elements out and process them, or pull them into your own collection and do them, and work on them yourself. And I think that actually does work quite well, because I've read a lot of code. It's like, what happens if a class exposes its internal data structures? Well, in practice, I don't like that, and there are ways to mitigate that. But the fact is that most code, if internal data structures are exposed, most code simply reads out of it. And so the fact is, if one of those is an unmodifiable collection, then in practice you don't get unsupported operation exceptions. Now, there are times when it can occur, and sometimes people will run into problems, but in practice, this does seem to have worked out fairly well. I actually did get a question about, what use are unmodifiable collections? Because the whole point of collections are to add and remove things. It's like, well, not necessarily. There's a very, very common use case, which is when you create a collection of things, there's a phase at the beginning where you gather together a bunch of data, and then you load them into a collection that is going to persist for the lifetime of the application, or it's going to persist for a very, very long time, or tied to some lifetime of some resource, like a database session or something like that. So in those cases, it makes the most sense to you have the data up front, load them into a collection, and the collection is itself unmodifiable. And so it's great, because then you can just park it somewhere, and you know that it's never going to change for the duration of its lifetime. And that turns out to be very, very useful. It is also very helpful for doing concurrent programming, because if you're never modifying something, then that doesn't mean it's thread safe, but it's an important step towards thread safety, because as we heard in the keynote this morning, if you have things that are shared and that are mutable, that is the hard part, and then you have to start thinking about locking. And so what unmodifiable collections allow you to do is to have sharing of unmodifiable, or preferably even immutable data, and you just don't have to worry about locking at all. Another thing that's not obvious from this is that a lot of data structures that are built for modification have space overhead built into them to allow for modifications to occur. And so if you never need to modify a collection, then you can rearrange the internal data structures and make them much more compact. I'll have an example of that to show later on in the talk. And so what I wanted to do also was contrast these with the, in the earlier code examples, I talked about the unmodifiable wrappers. So there are an existing set of wrapper APIs, and these new APIs provide unmodifiable collections as opposed to wrappers. And so I have an example of the differences on this slide here. So let's take a simple case where I have a list of 1, 2, and 3. And then the first list, I wrap it in the unmodifiable list wrapper. And so this, I forget when these were introduced. They were introduced very long ago. They might have even been introduced all the way back in 1.2, along with the original collections framework. So the unmodifiable wrappers have been around for a very long time. But they're just wrappers. There's still an underlying collection that might be modifiable. Now, list 2, on the other hand, is initialized using list.of 1, 2, 3. And that is an unmodifiable collection. There's no backing collection underneath it that can be modified later on. And so the similarities between these are they're both unmodifiable in the sense that if you try to call the mutator method either on the unmodifiable list or on the unmodifiable wrapper, then you're going to get the unsupported operation exception. However, there's a distinction here, which is that The first list is an unmodifiable view of the underlying list. And so if you still have access to the underlying list, you can modify it, and that modification will be visible through the unmodifiable view. So list 1 can appear to change as the program progresses if the underlying collection changes. Now, list 2, on the other hand, cannot be modified at all. So even though they were describing these collections using the term unmodifiable, there is this difference between an unmodifiable collection and an unmodifiable view that simply wraps another collection that might be modifiable. All right, so moving on to the next characteristic of these collections, nulls are disallowed. So this is, nulls. There's lots of talk about nulls over the year. Tony Hoare called this the billion-dollar mistake, and so Java has its own mistake in history with nulls. All references are nullable by default, and there are continued arguments and discussions about what to do about that. And in 1.2, unfortunately, the initial collections implementations and the most frequently used ones, like ArrayList and HashMap, do support nulls. And in retrospect, I think this is widely regarded as a mistake. And as evidence of that, every collection that has been introduced since then, or at least since Java 5, disallows nulls. And so in particular, the concurrent collections, but also other ones like ArrayDec, for instance, some of the lesser used collections. If you try to insert a null value into one of those collections, you will get a null pointer exception immediately. And so there's some reasons for that. If you actually look at the implementations, the early implementations like ArrayList and HashMap, there's a bunch of special case code in the inside the library to say, oh, if the value is null, then treat this differently, go through this different code path. And so that tends to slow things down a little bit. But it also presents something that semantically, it allows the application to do something that is semantically somewhat dubious, which is, I have a list of things, and one of the things is nothing. And it's kind of like having T and no T at the same time. It's a very strange thing to do. So sometimes applications want to do that, but my hunch is that it's usually sloppiness, and there are ways of avoiding nulls, putting nulls in collections, like using the null object pattern or something like that. And frankly, I don't think it is. I think there are ways that applications can successfully avoid using nulls in collections, and generally they're better off for doing so. So there are other problems with using nulls in collections, and this actually was introduced with 1.2, which is there's certain APIs that use null as a sentinel value in the API to mean something different from an actual value. So the typical case of this is map.get. So if you give it a key, you say map.get on some key, you get the value that that's mapped to. OK, great. What if that key is not present in the map? You say map.get on some key that's not present, the return value is null. Well, does that mean it's absent? Or does that mean that that key actually was present but mapped to null? So that's a flaw that was introduced in an otherwise perfectly fine API, except that the underlying map, like HashMap, allows null values. And so now you have a subtle problem in your code. If you're looking at that code and map.get returns null, then you have to think about that. It's like, well, have I ever possibly put a null in this map? Because if I have, maybe I need to use the contains key call instead of get, right? And then so you can see that this is a potential source of bugs if you put null values into a map. And then there's another set of methods on map, like map.compute and similar ones, where null is used as a sentinel value for actually removing entries as a side effect of a Lambda expression that gets called. It's a little too complicated for me to explain right now, but again, it's an example of how null is used as a sentinel value in the API to mean something different from an ordinary value. And so if you mix null in as an ordinary value, then it creates ambiguity in the API. And so we generally like to avoid ambiguity. Null is also very useful as a sentinel value for use inside of implementations. And so if you look at ArrayList and HashMap, which do support nulls, then they can't use null to indicate the absence of an entry, because null might really mean an actual value. So there's this substitution that has to go on in these special cases that go in. And so if you disallow null as a regular element or value, then what you can do is you have an array that contains the values. Null inside the implementation can unambiguously mean that there is no entry present there. For instance, this slot is available for reuse or something like that. And so what it does is it makes the implementation easier, which translates to more compact, space-efficient, and faster implementation that the library is delivering to applications. So I think there are lots of benefits for disallowing nulls. And this mostly continues the precedent that was set probably 10 years ago when, as I said before, most recent collections have not supported nulls. So anyway, so all of the new collections, the list.of, set, and map.of, if you put a null into the argument list, then you'll get an immediate null pointer exception. All right, randomized iteration order. So this is a biggie. There is a lot of history here. And so if you read the specifications for things like hash set and hash map, so the way hashing works is you take the key or the element, you compute a hash code, and then that's used for putting the element into an array at some arbitrary location based on the hash code. And so when you iterate over a hash set or hash map, then basically you take a sweep through the array and the elements come out in a fairly arbitrary order. And so if you read the specifications for things like hash set, it says that the elements, if you iterate over a hash set using, say, a for loop, the elements are iterated in no particular order. Now, in fact, all of this is well known. If you put a bunch of values into a hash set, they have well-known hash codes. Those hash codes use a modulus operation is performed to find an array index. And if you put the same elements in, they will come out in some fairly predictable order when you iterate the hash set. What's worse is that some of the values in the JDK have pretty bad hash codes. For instance, the string hash code is really mostly just a sum of the characters. So I've been using this recurring example of set.of a, b, c. Well, it turns out if you iterate a set with those values, if you iterate a hash set with those values, even though the specification says that the iteration order is undefined, in practice, every time what will happen is those elements will come out of the iteration in that same order, a, b, c. And so the problem is that programs tend to depend on that behavior over time. And you write tests. They say, oh, we'll load a bunch of data in and write some tests. And they write the tests, and it's actually pretty subtle to how it's not obvious looking at code whether it has an iteration order dependency. So it's pretty easy to say, okay, I'm going to load certain things, and I expect this set to have the A element and the B element, and so you might write some simple assertions that check to see whether those elements are in there, and that might easily have an iteration order dependency in it. And so we found out about this because from time to time, we change the iteration order of hash set. Like there's some hash code agitation that's performed to make things mix a little bit, and things end up in different slots in the hash table, and that changes the iteration order. And in practice, that tends to break people's code. And the problem is that we do change the hash map iteration order, and from our side, in the JDK side, we feel the specification says the order is undefined, so we should be able to change it at will. But the fact is, it breaks real code in the field, and people don't like it when we do that, and in fact, neither do we. The problem is, what happens is, we'll make some change either to improve efficiency or to fix a security hole or something like that, and it changes the hash map iteration order. We ship the release. It breaks a bunch of people's code. There's a whole bunch of discussion about this. a whole bunch of arguments. And so in the JDK team, we say, OK, sorry we broke your code. We're never going to do it again until the next release of the JDK. And then the cycle starts all over again, right? And so the problem is, one way to look at that is to say you should commit to the hash map iteration order and never change it. And so in fact, this is a lot harder than you think it is, because the hash code can be anything. And if you I mean, what it will do is it will preclude certain optimizations that we would like to make in the future. And in fact, the hash codes and the iteration order is fairly arbitrary. So how would you actually specify what it is? The only way to specify it is to say, you take the hash code, you apply this mathematical function, and then you modulus it with the array length and so forth. And so you basically would have to bake the implementation into the specification if you wanted to specify the iteration order. So instead of doing that, we're going to do exactly the opposite thing, at least with the new collections in JDK 9, which is to change the iteration order of sets and maps more frequently. So in fact, we will change the iteration order on every invocation of the JVM. And so it's actually pretty simple. A random number is generated at the beginning of when the JVM starts up, and that is XORed into the hash code. And so in practice, what will happen is if you say set.of a comma b comma c, and you print it out, those will come out in some arbitrary order. And then if you run that program again in a different instance of the JVM, those values will probably come out in a different order. And you might think, oh, that's terrible because it's unpredictable. But what it does is it will expose your code. I think I'm probably getting onto the next slide here, but it doesn't really matter. So the idea here is that the iteration order is predictably unpredictable. And what that does is it exposes your tests to changes in iteration order on a regular basis. And so if you're writing your tests and you do happen to have an iteration order dependency creep into your tests or your code, the hope is that you'll catch that very, very quickly before something goes into production. It also gives us a flexibility to completely change the implementation in the future, which we do want to do because there are many potential optimizations that we would like to deliver in the future. And if we're completely freed from the commitment to stick to a particular iteration order, then we can completely rearrange the internal data structures, and sure, it'll change the iteration order, but we don't care because it's randomized. So that's the real reason here. I wanted to mention this is not a new unique to Java thing. The Go language has maps that randomize the iteration order. And Python it's kind of interesting. They've gone back and forth on this. From 3.0 to 3.5, they actually did randomized iteration order. And I believe in 3.6, they went back to a different dict implementation that does have predictable iteration order. So it's interesting to see what's going on in the Python community, because there's a bunch of talk on both sides. And it's kind of the same thing, right? If you commit to an iteration order, then programs begin to depend on it. And so if somebody comes up with a new data structure that has a different iteration order, well, should we break their code? Well, but they're depending on something that they shouldn't have depended on, et cetera. It's exactly the same thing. So anyway, so we are moving towards randomized iteration order. So I should point out that the existing collections like HashMap do not have this. HashMap has its whatever iteration order it has, it will that's not randomized. However, future changes to HashMap might change the iteration order. So if you are concerned about preserving iteration order, you should use linked hash set or linked HashMap. OK. Duplicates are disallowed. So we check when we're initializing a set to make sure that set elements, there are no duplicate set elements or duplicate map keys. And I think the thinking here is that if you're initializing a collection and you're listing out all the elements, if there are duplicates in those elements, you've probably made a mistake. And so I think this is something that most other systems don't do. But the fact is, this does catch errors. So if you look at this code, this is kind of a revised version of the example I showed earlier on. It turns out that there's a duplicate in this. And so the obvious alternative is to say last one wins, right? Well, if you're putting a bunch of entries into a hash map, then the later one will overwrite the previous one. And so we could very well have map.entries, map.of and map.of entries have the same behavior, where later entries supersede earlier ones. But that would probably introduce a bug here, since there is a duplicate. And if you've ever had to, if you've been ever pulled out of bed at night because there's a bug in production, and you're trying to understand why there's something funny going on with your system, if you run into a problem like this at runtime and your eyes are blurry because you just got out of bed, it might take you a very long time to notice that there's a duplicate here. So, so instead, we decided, OK, since we have to take all the entries and hash them into a map, we can tell if there are duplicates at the time we're creating the map. And so it's probably a programming error that they're duplicates. So we throw illegal argument exception at initialization time. All right, so earlier on, I talked about the space efficiency gains that can be made from making a the collections unmodifiable. So if you have a collection that supports modifiability, you have to build some sophistication into your data structures to support that. If your data structure is unmodifiable, then we can compress it much more efficiently. So one of the things we do is we have different implementations under the cover if you have a small number of elements. So for instance, with the set implementation, if you have 0, 1, or 2 elements, then we have it's in the process of changing, actually, but we have dedicated classes that store set elements in fields. And above 2 elements, we have another set implementation that stores the set elements into an array. And so, so that makes things much more space efficient than a hash map is. So not only is the amount of space overall consumed, but since there are fewer different objects and they are less spread over memory, we get better locality of reference. So when you're traversing a data structure, then we have fewer cache misses and higher performance. All right, so let's take a look at an example of a couple, just something very simple, an unmodifiable set with 2 elements in it, and compare the space used between a hash map inside an unmodifiable wrapper, and then compare that to the new set.of implementation. So it turns out this creates a bunch of objects. Going from the outside, we have an unmodifiable wrapper around a hash set. Now, a hash set is really just a hash map where basically it doesn't care what the values are. It just looks at the keys. So there's a hash set instance and a hash map instance. And then a hash map stores its entries in a table. And then the entries in the table are node objects that contain the key, the value, the hash code, and a next pointer. So this is what the data structure looked like. So they're actually, for a 2-element set, you have all these objects, 1, 2, 3, 4, 5, 6. You have 6 objects. So now if you add up the space that you use by these, in Java, every object has at least a 12-byte object header, depending on the heap size and so forth, the JVM and the JVM implementation. But usually, I think this is a good rule of thumb: is a minimum 12 bytes per object, possibly an additional 4 bytes for alignment. And then 4 bytes for each reference field or primitive for most of them, and then doubles and longs also take 8 bytes. So if you add these all up, storing 2 strings in a set, that is, storing 2 strings in an unmodifiable hash set, takes 152 bytes. And this is not actually counting the strings themselves. This is pure overhead for the set data structure itself. And this is surprisingly large. Now, if you compare this to the new set implementation in set.of, this only takes 20 bytes. And the main reason is there's only one object. There's a new implementation under the covers called set2 that has 2 fields, and those 2 fields have pointers to the members of the set. And that's it. So it's a much, it still has the 12-byte overhead for the object header, but there's only one object. So anyway, so we can get a space savings. Instead of 152 bytes for a set like this, we have 20 bytes. And also there's no provision in this data structure for modifying it. So it's like, okay, well, hey, we don't have to worry about linked lists of nodes or anything like that in a hash table because we know that the contents are never modified. So we can get a lot of space efficiency out of the fact that these are unmodifiable sets, unmodifiable data structures. Okay, serialization, just a quick note on this. The fact is, a lot of people use serialization. There's built-in Java serialization and third-party library serialization. And so in keeping with precedent, all of the new collection implementations are serializable. There's a bunch of work going on under the hood to prevent information about the internal implementations from leaking into the serial form. One of the things we do in the JDK is we try to preserve compatibility of the serialized form from release to release. And so by default, if you just make something serializable, it exposes all the internals of your class. And so we wanted to avoid that. So we use the serialization proxy mechanism to have a unified proxy class. And that allows us to change all the implementations around without affecting the external serializable form. One thing that you should be aware of is these are new classes. They don't exist before Java 9. And so you cannot serialize one of these new collections implementations on JDK 9 and deserialize it on JDK 8. It simply won't work. So if you want to pass serialized data between JDK 8 and JDK 9, you have to use one of the collections that exists in JDK 8. All right, so that's what's going on in Java 9. So I wanted to talk about the future, that is JDK 10 or 18.3 or 10 or whatever version number it's named these days. So we're adding a few new APIs in JDK 10. And this is one of the things, is sort of an oversight in the initial round. If you want to make a copy of one of these guys, sometimes you have some computation where you want to add and remove and modify things, and then at a certain point you want to take a snapshot. And then you want to snapshot that into an unmodifiable data structure. So we're adding new methods which are essentially copy of that do that. And one of the nice things about this is inside the copy of implementation, it says, oh, if this is already an unmodifiable collection, it just returns that reference. So it avoids making redundant copies if it can be shown that that is safe to do. There is also new collectors that you can put at the end of a stream. And so you might have a use case where you want to create an unmodifiable collection, and the computation to do that is a stream pipeline. And so if you want to do that, then in JDK 10 there will be new collectors that will collect into an unmodifiable list, set, or map, and then the result of that is the same implementation that you got out of list.of, set.of, or map.of. So those are coming in JDK 10, which should release GA in I think 6 weeks or so. All right, so that's what's going on. I think the main theme of this is that the collections framework is pretty old. It was introduced 19 or almost 20 years ago. But I think the fundamental interface family, collection, list, set, and map, are still useful and continue to be evolved today and are still in heavy use. And so in JDK 9, we're continuing to enhance things along those lines. So we've added some factory methods that are not only convenient, but allow optimized, compact implementations. And JDK 9 is shipping, so you can get it from OpenJDK. You can get it from the OpenJDK website. And we are continuing to enhance the collections framework in JDK 10 and JDK 11. And so I'm available. I'll be around the conference today and tomorrow. I'm on Twitter. You can post with this hashtag if you have questions, comments, and follow-ups. Thank you very much. Probably, I don't think, do we have time for questions? Probably too short. Or
we have time for
maybe one
question.
Okay, quick question.
Okay, I take that as a no question. Sorry.
Okay, I'm going to ask you. So you got overloaded methods, lots of them.
Yeah.
But you've got one that adds 0 elements. What's the benefit of that compared to just an empty creating an empty set or an empty hash map or whatever.
Okay. Well, so okay. Well, so there's so why is there something like list.of with 0 arguments? Well, so the benefit there is that so there are 2 things. One, there's already collections.empty_list, and that returns something. But that is serialization incompatible with the list.of family. So that's one reason. The second reason is, and actually collections.empty_list shares this. There only needs to be one instance of the empty list. And so under the covers, if you say list.of with 0 args repeatedly, you actually get the same instance every time. So sometimes you really need an unmodifiable empty collection. OK, I think that's all we have time for. All right, thanks very much.